later also. Okay, so the last time I was about to do the anomaly by the Fineman diagram method, and it was clear that we were going to get too rushed on it. So let me just do a somewhat streamlined version, but nevertheless putting out the important stuff, just so you see these things. So basically, the thing we have, we're looking at an axial current, which is a singlet in all of its indices. So it's u bar gamma mu gamma 5 u plus d bar gamma mu gamma 5 d plus s bar gamma mu gamma 5 f. And the calculation we're attempting is this current, this is the J5 current, will be through a triangle diagram to two gluons. Okay. So the matrix element gets defined in the following way. You take nothing there, you take the current J5 mu 0 here, you take a gluon here, a gluon there, labeled by index A. B, it's the color index. This has momentum label Q. This one is minus K minus Q. So if we do this the way we've got it flowing here is K here, Q there, K minus Q flowing in, K plus Q flowing in there. Okay, so if I reverse it, it's minus K minus Q going out. Did I have that backwards? This is going to be I G squared epsilon 1, let's call this guy 1, that guy 2, alpha epsilon beta 2, these are starred, these are final states, beta some TAB mu alpha beta of K and Q. And the big test that we're after is K mu TAB mu alpha beta equals to 0. That's the conservation test. Okay. Well, the diagrams, there's actually two diagrams. There's the one, I'm going to label them because I actually want to say something about it. So I guess actually these lines are all drawn out is my trouble. They're all drawn out. K, Q, minus K minus Q. And this can be momentum P. This will be momentum P plus K then. And this will be P plus K, P minus Q. Okay, the other diagram, let's draw it. It's actually the safest to use the same momentum routing here, P plus K. And one of the issues, of course, is going to be how we choose the momentum. But in this case, this guy comes out with minus K minus Q, and this guy over here comes out with Q. So the momentum there is then P plus k plus q. Okay, and I guess I can skip writing out the Fineman rules for that. If you want, I can do it. The only trick in doing the conservation test, when we do the k mu on t mu alpha beta, there's going to be there's going to be a fermion trace. It'll be a k slash gamma 5 sitting inside there with propagators on each side. And you can see the propagators on each side. One's going to be p plus k slash, and the other is p slash. So you write this, the only trick of this is writing this as k slash plus p slash minus p slash. Okay? So that when you do that, the k slash plus p slash guy cancels that propagator, the p slash cancels that propagator. Okay? So you get down to something that has fewer propagators than you started with. And you always end up with this difference. It's something minus something else. Okay? That's relevant because I will write out the next one then. So there's a bunch of traces. You have to take the trace over the fermion indices and do all that. It turns into k mu ta mu alpha beta is minus 6i delta AB. That's the color indices. Epsilon alpha beta rho sigma integral d4k over 2 pi d4p over 2 pi to the fourth. And then there's 4 terms. It's p plus k plus q rho p sigma over this thing squared minus p plus k rho p minus q over p plus k p minus q squared. And then there's 2 more terms. I think that's enough to write out to illustrate this. At this stage, you can see 0 appearing pretty easily. These 2 differ only by, this one has p plus, so if I take p and replace it by p minus q, so this first term goes to p minus q, the second term goes to p plus k, so that they differ by just p goes to p minus q. So if we could shift p goes to p minus q, then they cancel. And so this is the famous shift of the integration variable that comes with this. And so the trick is to calculate what happens with that shift, or what's wrong with doing the shift. Okay. So here's the 1D analogy. So can we do the shift? Okay. If you have 2 functions, minus infinity to infinity dx, f of x plus a and f of x. Okay. That normally you would, since you're integrating over all x, you just shift that and call that 0. Okay? But if a was small, so doing it when a is small, we can write this as the integral from minus infinity to infinity dx of, well, if I Taylor expand that first one, I get f of x plus the term that survives is a f prime of x so that's at least the first term that survives. That's then the total derivative, so this turns into a f at infinity minus f at minus infinity. And so the shift is okay if those vanish. Okay, but it's not okay in general. Okay, and my favorite one, my favorite one is if I take the integral dx minus infinity to infinity of x. That's 0, but if I let x equals y plus a, this is the integral dy y plus a from minus infinity to infinity, which is equal to a infinity. So this is in case you ever want to get rid of infinity, here's the way to show that infinity equals 0. Okay, but so in our case, so the 4D generalization of this is I have the integral d4p, some function of p minus some function p minus l. We do the same thing. Let's Taylor expand that. This is then the integral d4p l mu df dp mu. Okay. Now this turns into then L mu. The volume integral turns into a surface integral, so it's the surface integral of f of p as p goes to infinity. Okay. So we're in more dimensions, so it's not just the endpoints, it's the surface integral out there. And yeah, to really define it, you do Wick rotations, but let's just quickly go through it. So in our case, yes. Sorry? This thing? L mu. dp mu, yes. This L, that's L. Okay. P is the integration variable. So I'm Taylor expanding this guy here. So I take f with L equals to 0, then the first derivative is respect to P, L mu, P mu. Am I misunderstanding your question? That's right. Okay, if you're trying to correct it, then well, we can ask why it's right. So basically, it's Taylor expanding this, and so it's like, should I go over it a little bit more? Do you see it or no? Oh, so it's okay? I'm happy to go more if you want. Okay. So I mean, this is like in 3D space if we had, some function of x minus x0. It would be f of x plus x dot del f evaluated at x0 equals to 0, etc. Okay, and then when we take I'm sorry, there's x0 there, and we integrate that by parts, we get the surface integral out at infinity. Okay, so in our case we have something that looks like this. There's some integral d4p 2 pi to the 4th p gamma over p to the 4th minus p minus l gamma over p minus l to the 4th. Okay, so if we were to try to do the shift out at large momentum, we're not going to worry about the k. What the large momentum is, it's something like that. Okay. This would then turn into, L mu integral d3 surface mu that's right. I've got p gamma here over p to the 4th. Okay. How to interpret the surface mu? We're going to interpret that as some scalar integral, which I'll tell you what it is. P mu over p. Okay, this is like if we did in spherical coordinates, we normally do integral dA is integral dA r hat. It points in the radial direction, so we're doing spherical coordinates. So this is just the equivalent of r hat, except in 4D. Okay. So, and when we see p mu p gamma, we're going to, since there's no other vectors around, we're going to replace that by 1/4 g mu gamma p squared. Okay. So our integral I gamma then turns into L gamma integral d4s, that's the surface thing. There's a 1/4 from here, and from that 1/4, and it's 1 over p cubed. There's p to the 5th, p squared up there took care of 2 of those. Okay, and at this stage, one does have to go to Wick rotate. We should have probably done it right at the beginning to do the surface integral. This turns into then L gamma over 4 I 2 pi squared p cubed over p cubed. So the surface integral in 4, actually, it should be 3. The surface integral, the angular integration is 2 pi squared instead of 4 pi. P cubed is the surface area equals I pi squared L gamma over 2. Okay. So there's how you do a shift. That's basically the shift. There is a non-zero shift if you have things that are linearly divergent. So this is linearly divergent. So d4p over p to the fourth is log. There's a extra power of p. Linearly divergent integrals are ill-defined, but this is the way to do the shift. The difference of two linearly divergent integrals. Yes.
So if those two integrals separately, I mean, were finite,
right,
then we wouldn't have to do this?
Right.
Okay, so since they diverge, we
Right.
have to do this.
Yes. So it's this bad behavior out at infinity that's causing the trouble. It's just like in this case here, if these things vanished at infinity, then we get nice finite. We could be getting a nice finite integral, so this thing would then vanish. But they don't, so this is also linearly divergent here because these things go to a finite value at infinity, so it has a linear divergence in it. It's the same thing we're doing right here. We have a linear divergence. Okay, so if you just carry out the calculation, do the shift, everything cancels except for the shift part. It turns into 3 over 8 pi squared delta AB epsilon beta rho sigma k rho q sigma. Okay, but that's not quite the end of the story. So this tells us that we are having some trouble defining this. It's still more complicated though. We could have started routing these things a different way. So back when we did this, I said, oh, it would be nice to put the momentum with the same momentum here and there. But, if somebody else had come along and said, I'm not going to do that, I'm going to make this one p plus k and this one p on the second diagram, you'd get a different result. So the routing was not unique. The second thing that you also have to watch out for is some of the gauge currents can also not be conserved. If you calculate with this routing, you also find Q alpha T mu alpha beta is not equal to 0. Okay. So that guy's bad news. We also have the gauge currents not conserved. The third thing is that if the gauge currents are conserved, then there's a unique answer for the last one. Okay, so there becomes then a unique answer for that. So the last part of the calculation is to say that we insist that the gauge currents be conserved because they're gauge currents after all. And then this forces the result that for matrix elements here, J phi mu is this 3 alpha s over 8 pi f mu nu f dual mu nu. Okay, so that forces the anomaly. Okay, so that's basically the U1 anomaly story. I plan to come back to it when I do the meson masses in QCD. In the QCD section, I'll build up the chiral Lagrangian, and we'll come back to this fact that this guy is not conserved, and show you some features of that. Okay. Any questions about what we just did there? Okay. I also want to do briefly the pi 0 to 2 gamma story. Okay. This is at the same thing. There's an anomaly that's related to pi to 2 gamma, but it's a different story. So you can just focus on the story here and forget the calculation of the anomaly. But here's some of the puzzles. If you we have an almost conserved axial current. Okay. The axial current that's going to be interesting is d mu J3 5 mu, which I'll write it as so d mu of u. Let's put a half out in front. U bar gamma mu gamma 5 u minus d bar gamma mu gamma 5 d. Now if you just take QCD, that would be conserved up to mass terms. Even if you add E and M, it's conserved. Okay. And the calculation just basically goes, there's a 1/2 here. It turns into U bar D slash acting that way, gamma 5 plus D slash acting that way on the U, gamma 5 minus the D terms. These guys can get converted into covariant derivatives. It turns that if you do that, the gauge pieces disappear, so the gamma mu, the A slash pieces just cancel exactly. You then commute this guy through. This guy turns into gamma 5 D slash with a minus sign. Then you use the equations of motion, and this turns into just IMU, U bar gamma 5U, minus IMD, D bar gamma 5D. Okay, so that's just playing games with the equations of motion. So this goes to 0 if M goes to 0. Okay. 2. So that's fact number 1. Fact number 2, it's easy to write an effective Lagrangian for pi to 2 gamma. Okay. So here is one. Here's the thing we do for pions is the kinetic energy pieces. U, so just like the sigma model, U dagger. We'll add a math term, which I'll talk more about. Trace mu plus U dagger m. That's a math term. And then you want a piece that connects pi to 2 gammas. So one that's chirally invariant, that has the right properties, looks like it has the right properties, is, well, let's put some coefficient here, Ca E squared, because it's electromagnetic, epsilon mu nu alpha beta, F mu nu, A nu, trace Q squared, U d mu U dagger plus U dagger d mu U. Okay, the Q squared's put in there because in the pi to 2 gamma decay, you've got U's hooking up to gammas or D's. And so the trace of Q squared takes the fact that there's Q up squared and Q down squared. Okay, so it's not that hard to convert that to a decay rate. This actually is a little bit tricky. This doesn't quite look gauge invariant right here, but it is if you do a gauge transformation on this and integrate by parts, the thing vanishes. So it actually is gauge invariant is fine. But the third step is the problem. So we have a symmetry, we have a perfectly good Lagrangian, but these clash. Okay. You can calculate J3 5 mu from Noether's theorem. From this. And it's just sort of like what you did. Actually, the one I'm writing out here is to be honest, I think the thing I'm writing out here is the left-handed one, which is just like the calculation that you did in the homework. So it's f squared, no, it's f to the first power, f squared it is, trace tau 3 over 2, u d mu u dagger minus u dagger d mu u. That's the left-handed piece that you found. And then there's another piece here, which is c pi e squared epsilon f a, and then it comes along here, it's trace q squared u tau 3 u dagger minus u dagger tau 3 u. So in other words, the derivative up there is just replaced by tau 3. Okay. So there's Noether's theorem, and then the clash is that if I take d mu j3 is not equal to 0 as m goes to 0. The first term works. That's okay. The second term fails. There's nothing that vanishes there. Okay. So, fourth step says, then the only way that this works, then C, I think I called it CA, has to be of order, its dimension, this has to be of order m quark, which in Python language, the quarks turn into m pi squared, so it's of order m pi squared over some cutoff squared, some scale squared, okay? So it would be okay if that were the case. So if CA went like m pi squared, we could then write a Lagrangian that satisfied this. But that implies a suppression of pi naught to gamma gamma of order m pi to the fourth over lambda to the fourth, which, you know, it's some number that's around 10 to the minus 3. So the pi to 2 gamma story has these ingredients here that this suppression was not seen. If you just put a typical number there of order unity, you get something in the right magnitude. You're not off by a factor of 10 to the 3. So, and the answer is that there's an anomaly in this, which is then d mu j axial 3 is alpha f number of colors 12 pi f mu nu f dual mu nu. These are now photons plus a mass term of and this, after some manipulation, tells us that it fixes the coefficient in the effective Lagrangian and agrees with experiments. Okay, so that's the story. So it's not quite how it's often told. It's often told that pi doesn't decay to 2 gammas without the anomaly. It would decay to 2 gammas, so just the decay rate's wrong by several orders of magnitude. Okay. Last thing for anomalies. Anyone want to ask a question, you're free to, but the last piece of lore that I want to pass on is that it contrasts global symmetries and gauge symmetries. With respect to anomalies. Okay? So global symmetries, of course, are just things like e to the I. Alpha was as a constant. Gauge symmetries are e to the I, some local variation. So the phase in the transformation depends on positions. The first one leads to conservation laws. The second one, of course, requires gauge bosons and dynamics. Okay. An anomaly in a global symmetry is okay. Okay. It just means that there's no conserved quantity. But an anomaly in a gauge symmetry is not okay. Okay? So and you can have a long and scholarly discussion about what goes wrong, but the answer is it goes wrong. It forces the gauge theory to be inconsistent. Okay. And there was a little period, I don't know, 20 years back, where people fought over whether you could have any gauge currents with anomalies and make sense of them. And the answer seems to be no. So it says that when you're constructing new theories, you always have to have no anomalies in any gauge currents. This is actually relevant for the standard model, which is what we're doing next. Okay, and the condition is the following. So if I take some triangle, A, V, V, okay, at each vertex there can be a little matrix that tells us it's either a number or maybe a matrix, so it could be, it could change an up quark to a down quark, so I, J, and K could all be different. The conditions that you come out with is it's the sum over I, J, and K. The axial charge, or the axial matrix QA IJ. Actually, I've written it wrong, so it's KI for the axial charge. So taking K to I times the vector charge, so V1, V2, they could be different. V1 IJ QV2 JK has to sum up to 0. Okay, so that if you put a bunch of fermions in here, IJs and Ks are fermions here, and this condition is satisfied, so you route the momentum the same way all the way through each of these, then the vertex, the triangle, disappears. Yes, the masses may be different, but the masses don't change the high energy behavior, so the high energy behavior works out. So this is then trace of QA, QV1, QV2 equals 0. So all these are, and this is actually, it's not always completely trivial. Let's do an example just to show you that it's not trivial. Let's take the 0 to gamma gamma vertex. Okay, so Z0 has an axial current. The two photons are vector currents. Okay. This says then the trace of tau 3 Q had better equal 0. Okay. What does that mean? Well, in our doublets, the doublets are going to be up, down, neutrino, electron. So the upper component is tau 3 is plus 1. So this gets summed over as the plus 1 is the neutrino times its charges is 0, plus the minus 1 component with leptons, the charges are minus 1 squared. That doesn't sum to 0. But if you add in the quarks, the plus component here is the up quark, so it's 2/3 squared times 3, because there's 3 colors of up quarks, plus -1 minus 1/3 squared times 3. 4/3 minus 1/3, 1 adds up to 0. Okay. So the anomaly condition here has been satisfied for z to 2 gammas. But actually it shows you that it's tricky. If I didn't have the quarks there, the standard model would not be consistent. If I didn't have the leptons, standard model wouldn't be consistent. You would think, you know, once you write out the standard model, you would have thought that it looks wonderful if I just forgot about quarks or just forgot about leptons. It's not true. There wouldn't be. There would be an anomaly in the Z0 coupling that would just totally destroy the theory. So it required this cancellation to do it. And that's actually where I'm going to start the standard model. Okay, so anyone want to ask anything about that? All right, if not,